Hi, my name is Karthik Taluri, and today I will be presenting my project on efficient robotic arm grasping using mask RCNN and principal component analysis. I will be utilizing mask RCNN and principal component analysis to implement an efficient grasping mechanism for robotic arms, comparing the performance of different object detection and segmentation algorithms and exploring various applications of the technology. The specification is split into various sections which explain about the implementation and evaluation process and the time frame in which they will be done. It helps readers understand details involved in working with vision-based robotic arm systems and comparing various architectures. The aims include achieving high grasp accuracy for various objects and comparing the performance using the GRASPA benchmarking framework, implementing and comparing various object detection and segmentation algorithms in the context of robotic grasping, explaining various applications in which the technology could be used. The objectives include implementing mask Gaussian model in image segmentation and other object detection algorithms for comparison, using the PCA axis to find an appropriate grasping point and observe the forces to correctly pick up the object, evaluating and recording the results in a systematic way and improving performance on each iteration, comparing the results with other solutions too. These are some of the papers that I have read during the past few days, some of which include Mask RCNN, which explains the working of the Mask RCNN framework, which I will be using and evaluating. Other papers mentioned after have explored different approaches and techniques in robotic arm grasping, which I will be using to compare and evaluate results. Here is a high-level overview of how Mask RCNN works. Firstly, the backbone network. Mask RCNN starts with the backbone network such as ResNet or VGG, which is responsible for extracting high-level features from the input image. The backbone network typically consists of multiple convolution layers and is pre-trained on a large dataset such as ImageNet to learn generic visual representations. Region Proposal Network. The RPN is a separate network that operates on top of backbone network. It generates region proposals, which are potential bounding boxes that may contain objects of interest. RPN examines anchor boxes at different scales and aspect ratios and predicts the probability of each anchor being an object or background, as well as defined coordinates of the bounding boxes. Region of interest align. Once the region proposals are generated, ROI align is applied to extract fixed size feature maps for each proposal from the feature maps produced by the backbone network. ROI align avoids information loss caused by quantization and performs bilinear interpolation to obtain accurate pixel level alignments. Mask head. The additional branch in mask RCNN is the mask head. It takes the ROI features and performs fully convolutional operations to predict a binary mask for each region proposal. The mask head uses a pixel-to-pixel segmentation approach where each pixel within the proposed bounding box is classified as either foreground or background. The main steps in finding an ideal grasping point using principal component analysis is the covariant matrix. The covariant matrix represents the relationship between the different dimensions of features of data. The next step is to perform eigenvalue decomposition on the covariance matrix. Eigenvalue decomposition is a process that decomposes a square matrix into eigenvalues and eigenvectors. Principal axis selection. The eigenvector associated with the highest eigenvalue represents the principal axis along which the object has the most significant extent. Ideal grasping point. This principal axis provides valuable information for determining the ideal grasping point for the robotic arm. It allows the arm to align itself with the object's major axis or grasp it in any way that maximizes stability, dexterity, or other desired criteria. I have also implemented mask CNN algorithm to plot principal axis of the detected image using its centroid, researched about various applications in which the technology could be used, and tested, read papers on evaluation techniques and key concepts to improve understanding, and also set up the MoveIt ROS software on my system to implement solutions. The image here shows each of the segmented object and principal axis drawn from the centroid based on the calculated eigenvalue and eigenvectors. Coming to the implementation, the image source here collects frames of images including the information about depth, and mask RCNN is used to segment the image. Using the segmented image, we could find the principal axis using which we find the most efficient grasping point. We repeat the first two steps multiple times by changing the segmentation algorithms and sometimes trying on a new implementation. Some of the softwares I'll be using are MoveIt ROS Neotech. It is good for the tasks of motion planning, robot manipulation, simulation, and virtualization. It seems like an ideal version since it works on Ubuntu 20.4.04 and has a wide community. It is also compatible with Python. And finally, PyTorch. It has pre-trained machine learning models, including MaskRCNN, which could be configurable in multiple ways. It is much easier when performing hyperparameter tuning or when there is a requirement to train the model. The image here shows the user interface diagram of the MoveIt ROS framework. Some of its important parts are RViz. It's a 3D visualization tool for visualizing the robot's configuration, planning trajectories, and simulation motions. Planning Scene represents the robot's environment, allowing users to define obstacles, kinematic properties, and specify motion planning goals. OMPL is the core motion planning engine with various algorithms to generate feasible paths for the robot. And Planning Pipeline, configurable pipeline to combine planning components and algorithms optimizing planning performance. Some of the data sources that I will be likely using are the DexNet 2.0. It's a synthetic grasping dataset. Big Bird. It has point cloud and depth information for real objects. And Jacquard dataset. It has RGBD images with plotted principal axis. There seems to be no ethical approval required as it doesn't involve human subjects and uses publicly available datasets. I will be testing my model and comparing it with the performance measured in the following methods and evaluating the results for the performance. Reachability score. We measure the number of instances that the robot reached where the object is located and total instances. We only consider the instances where the pose and orientation errors are smaller than its threshold. Graspability score. Each robot has different graspability score for a particular object. It defines if the robot can bear the weight and if the dimensions of the object can be graspable. Grasp quality score. It relies on grasp run space and object run space. The score is calculated using robotic simulations, which could be done using MoveIt ROS framework. GWS is obtained by changing the robot's pose multiple times and averaging the results. OWS is the best grasp space for the object. Binary success score. An object is successfully grasped if it could be lifted to a certain predefined threshold height. It is done for multiple trials and the results are averaged. Grasp stability score. It defines the number of positions the robot can move the object after lifting, divided by the total number of positions. It defines the number of points it reached with the object. And the final per object score is based on whether we are benchmarking objects in isolation or in clutter. We don't include the object avoidance score when this object is in isolation. The table here shows the formula used to calculate each of the evaluation metric and their meanings. There are various performance measures using which we could evaluate the solution. GraspR seems to be a good solution for evaluating performance of rigid bodies. It provides a quantitative measure on how successful a grasping task is implemented by considering various factors related to the grasping process. Here's how GraspR can be used for evaluation. I would be using the following metrics for evaluating the score. I would be benchmarking the scores in a clutter. I would implement various robotic arm frameworks and segmentation algorithms and compare those metrics with the MaskRCN framework using PCA. I expect the system to be considered successful when the proposed framework achieves better results than other architectures mentioned in the background reading section. The following table shows some of the algorithms that I think could improve using MaskRCNN. The first paper proposes using synthetic datasets with various lighting conditions and grasping points. This dataset was used to train probabilistic models to predict an accurate grasping point. The second paper describes detecting a specific object and using its detected edges to grasp and move it to a specific location, but it only works for a specific object. The third paper uses RGBD camera to acquire depth information and uses MaskRCNN to implement semantic segmentation. It focuses on object detection and grasp planning, where it first identifies specific objects using segmentation and maps it to the 3D model using geometric primitives. The fourth paper uses a random forest model to detect grasping points. I will be comparing the performance of these models against their specific evaluation metrics and improve the results of my model. This is the Gantt chart showing the project plan until the submission of dissertation, and I believe the dissertation phase and the evaluation phase take the longer time than the implementation phase. Some of the common risks that I've identified are hardware failure, software failure, running out of time, and testing of errors. Hardware failure leads to long time in training the models, for which I'll be using university systems or external servers. Software failure leads to delay in implementation, for which I'll be spending more time on debugging. If I run out of time, it creates partial completion of projects, so I'll have to make my plans more dynamic with some buffer in the end. If there are errors in testing, I will be repeating evaluation multiple times, so I have to be more careful in making evaluations. These are some of the references I have used for project specification. Thank you for listening.